the AP exam, about a third of the AP exam is graphing calculator. And a lot of the graphing calculator in AP Calculus is the integral part of the course, which is the course area that we just learned most recently. So what we're going to do is adapt and use the graphing calculator to answer some of the following questions that were from a free response part of an exam over the past few years. So one of the main areas of our graphing calculator and one of the main concepts we're going to be using is under math. So we're going to be using the math concepts, and we're going to be using nderive and FINT for derivative and integral. So we're going to be using those features, and we're going to be using a lot of features involving graphing. So we're going to be plotting points, finding zeros, calculating derivatives, and integrals, all from graphs. So being able to adjust your window is another key part. So let's consider this first function. So what we're going to do is go to y equals, and we're going to type in x squared cosine x squared. And I always like to, because I'm kind of cautious, make sure my calculator is in radian mode. Because if you're in anything other than radian mode, your answers also aren't going to match the AP exam. So what we want to do is start with the basics. We're going to plot the function so that we can see the function. So if you hit zoom 6, that is not a good plot for this graph. We can see all this craziness on the outside. But what we should notice is that the graph is doing some stuff in here that's very different from the oscillations that are happening on the outside. So I might want to bring my graph in, and I'm going to trace it out so I can see a little bit of that. But it looks like, -10 is even going to help me a little bit, but let's go to -5 to 5. So that's pretty good. Might even be able to go in a little bit more, but that initial window of -5 to 5 from -10 to 10 isn't bad. And then it says, now suppose you were told to examine the function on the open interval -2 to 2. Well, if I'm doing the -2 to 2 interval, I'm going to shrink my x's down to -3 to 3. I always like to leave stuff on the ends. And it looks like my highest y value is here. So that's at about 1, 2, 3, 4, 5, 6, 7, maybe 8. So I might change my y windows. Again, there's not much happening down here. So that my y window now is like -4 to +8, just to try to zoom it in. So I can see that max, I can see that min, I can see what's happening in here. I think that's a pretty good window. Find the zeros of the function on the open interval -2 to 2. So to find our zeros, we're going to go to second trace. You're going to go to 0. Now we're only going -2 to 2. So here's definitely 1. And then this one, if you look, it's at -2.17 near that 0. That's outside my interval. So I'm not going to find that one. I'm going to start over here and find this one. So I have a 0 at -1.253 because I need those 3 decimals. Maybe I go second trace, go down to 0. I can't tell if there's one at 0, so just to be sure, I'm going to go to the left, I'm going to go to the right, and I'm going to guess. It's thinking really, really, really hard. So it said no sign change. Zoom in a little. Because I feel like, actually, I guess I could just go to my table, right? So let's plug in 0. Yeah, I felt like 0 was 0. So there's no sign change, but there is a 0. That's a error on our calculator's part, not seeing a sign change because it's a repeated root, so it goes right back up. So calculator error. Okay, then we're going to go over here and we're going to find the other one, and the graph's symmetric, so I'm going to guess it's at positive 1.253. So I have 3 zeros of my function, and then it says find the maximum value of the function on the open interval. So the max in this case, again, we're not talking about the max finding it with the derivative, we're talking about the max on the actual graph. And what's kind of nice is the graph is symmetric, so we only have to find this once because the max that happens on this side is going to be the same as the max on that side. So it's happening at positive 0.927 as well as negative 0.927, and the y value is 0.561. And then it says find the minimum value on the open interval. So now it's a little bit different. My minimum is going to be way down there. So we're going to go to second trace. We're going to go to min. We're going to go to the left. We're going to go to the right. We're going to hit enter. And I get negative 3.288. And then it says find the value of the function at x equals 1. So in case you don't know this, what you can do is go second trace. You can go to value. You can type x equals 1, and it will give you the value on the graph. You could also go second table, and if you're in ask mode, you could type in 1. Now, if you're not in ask mode, you could scroll because that's a perfect number and it would be there anyways. And then it says calculate the derivative of the function at y prime of 1. So remember, our function's in y1, so I'm just going to hit second quit, math 8. So I get my derivative. I'm going to hit d dx, vars, y vars, function y1. And then we're evaluating at 1, so I'm going to plug a 1 in there and hit enter, and I get negative 0.6023. Then it says find the equation of the tangent line to the function at x equals 1. Well, the tangent line is y minus y1 equals m tan x minus x1. And in this case, my x1 is 1, my y1 is that 0.503, and my m tan is that negative 0.6023. So it'd be y equals negative 0.6023. X minus 1, and then over here would be y minus that, so we're just going to add that to the other side to move it over, so plus 0.5403. Okay, graph the derivative of the function. So if you wanted to graph the derivative, what you can do is actually almost take this piece right here and mimic that idea in y equals. So you're going to go to y2, we're going to go to math 8, you're going to hit dx, you're going to go to vars, y vars, function y1, and then instead of equaling to a number, you're going to put x, so it evaluates the derivative at all x's. And then if you hit graph, it's going to put the derivative function on there. Now, I didn't bring my fancier calculators home that have colors. If you have the newer LED ones, then it would be like blue and red. Those ones are just hard to record, so I'm using one of the older calculators. Okay, and then it says find the extrema of f prime. So the extrema of the derivative are going to be able to be found. Now what you could do is turn off the original function. So you could turn off that original function and only now see the derivative. But what we notice happens is now when I turned off that original and I only see the derivative, I'm way up here. So I'm going to have to change my values as well. However, I have a max and a min on the graph as is, so let's find what's on there now. So it says a max at, so my max is at 0.6095. And then I'm going to have a min. I'm going to have a min down here. And I will find it even though the y is off the screen. I have a min at 1.554. And then we have another min over on the other side. So we're going to move our cursor all the way over. And that's what I was talking about earlier. The hardest part of the AP exam with calculator questions is actually manipulating the calculator. So we have another min at negative 0.6095. And I'm going to bet we have a max at positive 1.554. So let's just move over and find out. Enter. Cursor. There you are. So you just always want to make sure your two arrows are pointing in at the value you want to find. And there we see a negative 1.554. Okay, and then the bottom part, calculate the value. So you could do this in one of two ways. You can do it on the graph. You can hit second quit. You can go to math 9. So we're going negative 2 to 2 of the original vars function. So we want to get y1 in there with respect to x. And you get negative 2.318. And then this is a question from the 2008 exam. It says the derivative of the function f is given by f prime equals this. So that's now my derivative. How many points of inflection does the graph of f have on the open interval? So if this is the derivative, the next derivative, those zeros with sign changes would give you your points of inflection. So that's what's graphed here currently. So if you count 1, 2, 3, 4, 5 zeros and 5 sign changes, because sign change, sign change, sign change, sign change, sign change, that means that this graph has 5 points of inflection. Okay, example number 2. So this is from the 2000 exam, which is really scary to think is older than you. But let R be the shaded region in the first quadrant enclosed by the graphs of y equal blank and blank and the x-axis. So look, if this is the question on the calculator exam, and this is question 1, before I even read through it, I am clearing out whatever's in my calculator and I am typing these two functions in. So I'm going and I'm hitting second e to the negative x squared. And I'm typing in 1 minus cosine x. Just putting them in. And then it says that it is enclosed by the y-axis. So that tells me my x min is 0, because y-axis. When answering questions, be sure to find any expressions, equations, etc. So it says find the average rate of change. So average rate of change. So that means, to me, I'm thinking, okay, rate of change, And then I'm thinking average. So I already know my interval. So the average rate of change is going to be y of 5 minus y of 0 all over 5 minus 0 for that function. So go to your table. That's my first equation. So I'm going to plug in 5. I'm going to plug in 0. So when I plug in 5, I got 1e to the negative. So that's kind of gross. So maybe now I have to say, all right, I need second e negative 5 squared minus, then you can actually like hit enter and bring it down and then just change the 5 to a 0. So you get negative 1 divided by 5. So you can write down 0.2 or negative 1/5. And apparently my eyes are really bad because that is 0.5 and not 5. So that's if it was a 5. Now let's change it to a 0.5 because my eyes are terrible. Wondered why they didn't give you a good number. So now we get 0.7788 minus 1 over 0.5 minus 0. Which is negative 0.4424. Then it says, where in the interval is the instantaneous rate of change equal to the average rate of change? Okay, guys, instantaneous equals average, MVT. MVT. Instantaneous equals average is MVT. So the easiest thing, though, for you to do, if this is a calculator question, the average rate of change we just found, it's negative 0.4424, and we want to know when the instantaneous rate of change is equal to that. So what we could do is find the derivative using these features of the calculator. So what I'm going to do is I'm going to turn off the cosine graph. I'm going to go math 8. I'm going to put D, I'm going to put vars, y vars function y1 for all of x's, and I'm going to put in that negative 0.4424. And I'm going to actually even turn off the original graph because what I want to do is know when the derivative equals the average rate of change. So that's what I'm going to look at. So my window is 0. 2.5 is pretty good. It's probably not going to be in the negatives, so we're fine. So we want to know, okay, when do the two graphs intersect? So here's my derivative, and here's my slope. So set, trace, intersect. Enter, enter, enter. So they intersect at 0.2336, and we intersect again over on the other side. However, when I go all the way over to the other side, what am I noticing about my x values? They're too big because it gave me this interval here of 0.5. So it says where in the interval is the instantaneous rate of change equal to the average rate of change. So I would say at x equals 0.2336, the instantaneous rate of change equals the average rate of change. Find the tangent line to each curve at the point of intersection. Find the tangent line. So tangent line is y minus y1 equals m tan x minus x1. So I know I'm writing an equation of a line. So find the tangent line